In this video, we're going to start to look at how we can calculate the length of curves and using integration to do that for us. So before we do that, let's just take a look at some arbitrary curve that we're going to say is defined by y equals f of x. And let's say we partition this into many different x values here. All right, and we can partition it to some arbitrary number, doesn't matter, from a to b. So we're going to start at some point a over here on the curve, and we're going to go to some point b over here. And if we just look at one partition, one little segment right here, we can say that, you know, we could approximate that length by looking at the change in x and the change in y. All right, and if we look at the absolute value of that to give us this triangle. So from this point right here, from x sub k minus 1 to x sub k, or you can, it doesn't matter what your index is, we're just going from one x value to another, we can approximate that length there using a triangle. If we redraw that triangle here that we had pictured earlier, where this is our right angle and this is delta x and this is delta y, we can say, well, what is this length? And remember, this length here is approximating the length of the curve there. It is a line. It's not the exact length of the curve, but it's an approximation. And we can say, well, using Pythag, this is going to be delta x squared plus delta y squared. So if we say our length is this square root expression, we can use a little bit of algebra. Oh, sorry about that. We can use a little bit of algebra to divide everything by a delta x squared and actually factor that out. So I'm going to rewrite this as the square root of the quantity delta x squared, and then I'll get a 1 plus delta y squared over a delta x squared, all underneath the square root. And we can see that, well, the delta x squared, square root of that is just going to be delta x. So I'll get the square root of 1 plus delta y over delta x, that quantity being squared, times a delta x. Now, knowing what we know about integration, you can see what's coming in that, okay, this is an approximation for an arbitrary partitioned portion of the x-axis. Well, let's make that arbitrary portion. Let's take this delta x and let's have delta x approach 0. And so what happens to delta x? When it approaches 0, it approaches this differential dx. And so that means that this L, which really, that's our tiny little L, so we'll call that our DL, our infinitely small but not 0 DL is going to equal the square root of 1 plus, well, that dy is going to pop out because the delta y, if delta x is approaching 0, then delta y is approaching 0, so that's our differential dy. So we get dy over dx squared times dx. And so if we want our total length, L, the total length of the entire curve from a to b, we just want to integrate. So we integrate this from a to b, and we get this square root of 1 plus, well, what's dy over dx? That's the derivative. That's the first derivative of our function, squared. And we're integrating that with respect to x. And so that gives us our formula here to find the length of any curve over some interval, a to b. So as long as we have a continuous function, and that is important that we're continuous here, as long as our function is continuous and the first derivative is continuous, then we can find the length by taking this integral. Now, it's going to give us some nasty integrals at times, but it's at least doable, you know, if nothing else, with the help of a calculator. So let's take a look at an example here. Let's say we have the function y equals x to the 3 halves. And we want to find what's the length from this point here at x equals 0 to x equals 4. Okay, so let's take a look at that. We need the length is going to be the integral from 0 to 4 of the square root of 1 plus, oh, well, we need the derivative squared. Well, what is the derivative? Well, if y is equal to x to the 3 halves, then y prime is equal to 3 halves x to the 1/2. And then y prime squared is going to equal 9/4 x. So we just add in plus 9/4 x dx. Now, if we want to actually evaluate this by hand, we're going to have to use some techniques that we're going to learn later on in the course. So for right now, we can just plug this into our calculator, and we get the length to equal something like 8 times 10 radical 10 minus 1 all over 27. And if you want to know what that is approximately as a decimal, it's something like 9. It's like 9.0, I think 7 or something like that. So it's just under 10. Okay, so the length of this curve from 0 to 4 is about 9. Well, we can look at this in any type of shape, and so let's look at 1/8 of a circle. So we want to go from, say, here to here along our circle. Well, looking at 1/8 of the circle, our function here is y equals a squared minus x squared. All right, well, the square root of a squared minus x squared, that defines this top curve here. All right, that's our y function, that whole top curve. And if we want to find 1/8 of it, we want to look for the length from 0 to this a over radical 2. So in order to do that, once again, we're looking at our function. F of x is equal to the square root of a squared minus x squared. Okay, and we need the derivative of that. Well, the derivative of that, we're going to get 1/2 this quantity, a squared minus x squared, to the negative 1/2 times negative 2x. All right, so not necessarily a nice derivative, but we can find the derivative nonetheless. And we can find the length by taking the integral from 0 to that a over radical 2, and then the square root of 1 plus the derivative squared. Well, if we square this, let's simplify this first before we do that. This will give us a negative x times this a squared minus x squared to the negative 1/2. And so when we square that, that negative is going to go away, and we're just going to have x squared, and then we're going to have over, so I'll write it here, x squared over this a squared minus x squared. Now, once again, we will learn techniques in which we can integrate this. For right now, we can't integrate this other than plugging it into a calculator. And so plugging it into a calculator and knowing that this is 1/8 of a circle, we know what the length should equal. I mean, the length of the entire circle is the circumference, which that's going to be 2 times pi times a. Divide that by 8, and we're going to have pi over 4 times a. And that is what we would expect. And in fact, when we learn these techniques of how to deal with these types of integrals, we'll find that we will, in fact, confirm this result of pi over 4a. Now, this arc length formula works for writing functions as a function of y as well. X is a function of y. We do the same thing. We're just looking on an interval from c to d on the y-axis, and so we take the derivative of y, of the function of y with respect to y, and we integrate with respect to y. So all the stuff stays the same. So we could look at this curve, say y equals x to the 2/3, and that gives us x equals y to the 3/2, and this is the exact same problem that we just did before, in that we're going from 0 to 8 on the x-axis, but that's really 0 to 4 on the y-axis, and so we'd get the same result that we had before there. This can be helpful for us when we want to find a function that's easier to integrate. So for instance, looking at this function here, y equals the natural log of the quantity x plus the square root of x squared minus 1, well, taking the derivative of that gets kind of nasty, and then integrating that after it's squared and inside 1 plus that inside of a square root, it gives us a very nasty integral. However, if we write it in terms of x, we get something that is easier to differentiate and easier to integrate, and so that can help us out a little bit here in finding these curves. So we're going to use this formula, use the integration. When we come up to a nasty integral that we don't know how to integrate, at this point, we're going to use the calculator to do that. Later, we'll learn techniques on how to actually do some of these integrals by hand.